video. There's chickens somewhere. And get out of here. You don't know what I'm talking about, do you?
No, I saw the video.
Oh, okay. So, maybe some of you in the back don't. But anyway, so I will upload the videos as we make them on top of the previous ones. But if you have subscribed to the other channel, that's not the right channel. Anyway, you'll figure that out. Okay, what am I supposed to be doing is, all right, probability. We talked about probability distributions, and I had kind of, come in here and fix that anyway. So I had this example of flipping a coin, and to introduce you to probability, not that I need to do that, you know how to flip a coin. What I was trying to get across last time was when you flip a coin a whole bunch of times, it may not quite be as straightforward to deal with as just a single flip. You know, small children understand the flip of a coin, right? So, and I also presented a very scientifically immature way of thinking about this, to say that the coin absolutely has two even sides, but then to state that I expect 100,000 flips to have exactly 50,000 heads and 50,000 tails, an exact split to mirror the exactness of the coin itself, is unreasonable. Right, so I drew a little distribution last time of what that actually looks like. An exact 50,000.0000000 number of heads and equal number of tails will happen only 0.3% of the time. And again, to think in a scientifically immature way, you would, if you get more heads, you'd say, well, I guess it's the coin is heads heavy. The head side of the molecule is bigger than the tail. You're wrong. So, and the answer, of course, is that we allow a little bit more or less of an observation of heads. You know, 50,000 heads plus or minus, I think it was 100, would be observed 50% of the time. So anyway, again, I'm just trying to calibrate you. I mean, I think that's kind of instinctual. But then where we get into things that I'm guessing is new territory is how do you deal with that mathematically, right? Again, physical chemistry, I want equations, the equal sign, you know, this isn't a little wiggle, right? It's not a sort of. In physical chemistry, I want this to be equal. So how do I deal with that distribution? How do I deal with the fudge factor in a way that is mathematically perfect? The answer is you have your distribution, the thing that makes it make sense. You're going to get probability out of it, but you're going to have this in-between, which is a probability density. What that is actually that Gaussian curve that I drew last time for a number of heads. I'll just call it H. And the flip. And again, I did 100,000, so at 50K, it was centered at 50K. So this bell-shaped curve was the probability density. Now let me tell you a little bit more about probability densities. Why is it a density? Let's do a units analysis. What are the units? So I'm not going to write that down. What are the units of probability? It's very simple.
Percentage.
Percentage. Okay, but what kind of unit is a percent? If you're confused, percents are fractions. Mass over mass.
Unitless.
Unitless, right? Dimensionless. So no. And yes, it is still a percent, but a percent actually has no formal units. Okay, now we're going to wean ourselves off of coin flips. Let's say that this is energy. Y will be energy. We're going to be doing distributions of energy. So Y is a property, and again, forget coin flips, that was just a little tool. Now it's energy. So the units of a partial, we talked about this last time.
In this case, they have units of flips.
No, we're not going to do flips. We're going to do energy. Let's just forget the coin at this point.
Joules.
Joules, right? So it has units of joules. Okay, now see, this is where it gets a little funky. This has units of what?
1 over joule.
1 over joules.
Yeah, there you go. I'll write it out. Okay, right. Now you see why it's called a density. Grams per liter, right? That's a density. That's actually the density, right? And then there's actually all kinds of densities. There's energy density. You've probably heard that word many times. So probability density gets its name because it has units of inverse whatever the spread is. So that's where it gets its name. It also is not like a probability because of that. Probabilities don't have units, probability densities do. And so that's why it can get like, it's unfortunately, you know, we understand probability incredibly well. Partials are whatever, they mean that I have integrals. Integrals are not terribly difficult to understand. I always do integrals, I mentioned this last semester. I like to do an integral by, okay, here's the function, the derivative of what is that function? That's, I have to reverse engineer, that's how I do integrals in my head. Okay, so none of it's particularly difficult, but what the heck is that, right? So we're going to spend the next 2 weeks on what the heck is that. And the only thing about integrals, again, probability is something a child understands. It's great when we can explain everything that way. It's just that we have this integral, which is like a degree of separation. And often probability densities, once you get used to them, especially when they're just things like bell-shaped curves, that's not particularly hard to understand. And we talked even a little bit about areas under curves like that, so I won't repeat that. Actually, here, let me do a different type of review to remind you of, okay, so let's talk a little bit more about the properties of this thing. And as I mentioned, let's forget flips now because that's a little bit childish. I just wanted you to make sure that, you know, that you're like, yeah, I know what a probability is. Okay, again, I'm going to now switch to energy. I don't know what it means to have a partial of a flip. I can't, when I do some real deep science stuff, I will occasionally see things like the partial of a molecule, and I really, that's kind of confusing, but energy, that I'm comfortable with. So, okay, so we're going to switch to energy. We have a probability density of energy. I'm going to forget the subscript, so anyway. Now, what am I going to integrate? How about I integrate from 0? Of course, they have units of the partial. And again, yes, 1.0. Right, now if I throw this at you without even defining anything, you should know it's 1.0. Now, if you're like, what the hell just happened? Remember that the output is a probability. That means it'll be between 0 and 1. 1 is 100%, 0 is 0%. How did I know it was 1.0? 100%. It helps to be able to put this mathematical expression into English language. I did that a zillion times last semester. I can do it a few times this semester. Unfortunately, not always, because quantum stuff, this is all a prelude to quantum. In this case, I can do it. Don't expect me to do it very often. The English language saying of this equation is, what is the question is, what is the probability a molecule has somewhere between no energy and infinite energy? Huh? The answer is 100%. It either has something or nothing. Yes, of course it does. That's true of everything. So that one's particularly easy to understand. Okay, now next thing. Let's say that energy...
Hey, Professor, how do we know that you're talking about probability density instead of probability if there's no density substrate?
Because I'm going to forget that's coming to be blunt, I'm going to forget. And number 2, I'm integrating it. It's a density. Yes, and you will not see me do anything else, right? This was just I kind of started here to get you here, and so we're staying here from now on. We're not going to I'm not going to work in reverse from now on. We're going to always do probability densities.
Okay.
I know, I can already tell I'm just going to forget that subscript every time. I'll try to remember. Okay, next cool thing, and you're going to be doing this a lot too, by the way, it's relatively easy. I'm going to go over this in great detail next lecture. So this is a probability distribution of energy. You can imagine that the equation is something like E to the energy over KT. In fact, that's that's almost exactly right, not quite. But now, wherever I see energy in this equation, and you will see this next lecture, if instead you wrote this, if instead you wrote that, it's kind of cool because the equation is still exactly the same. It's just that it doesn't have E, it's got a V in it. Well, now it's a probability distribution of velocity. The tricky part is actually here. We'll go over that next time. All right, now let's also translate the, I want to make this 1. So now I got to translate the limits. You got to be a little careful about that too. Again, we're going to cover that Friday. Well, but you kind of know this. What do you think? What are the limits? Now this is net velocity. Now the upper limit's easy. All right, that'll be infinite, and we'll work in SI meters per second. What's the lower limit?
Negative infinity.
No. Net velocity. Net velocity is the square root of Vx squared plus Vy squared plus Vz squared. So 0. Right. You cannot have a negative net velocity. Just to remind you, tell me if you guys have trouble seeing this. Tell me, is this invisible? It's not?
I can see it.
Okay, cool. Don't forget that your vector, this and that. Of course, you cannot turn this negative because it's a square root. Okay, so as a result, the lower limit is 0 meters per second. Okay, in English, what is the probability that a molecule is not moving or is moving? The answer is 100%. Right? See? Not terrible. Gets a little terrible once I start putting equations in there. A question.
So why are you just considering kinetic energy for the energy and not like potential or anything else?
Well, now, because I'm about to discuss that.
Okay.
So, yeah, let me, literally that's on my next agenda. I just want to show, at least for now, and actually what we're going to do is I'm about to show you what the distribution function is for energy, and then we're going to translate it into velocity. So I'm doing that right now. The main thing I want to get across is that you can do this, that you can turn, I've always been fascinated with this. This is a distribution of energy, and so is this. It's the same thing. I just changed the letters around. But it's meaningful to a person, but to the math, it's the exact same equation. It has the same result after all, right? As long as you get the limits right. Okay, anyway, all right, now, what do I want to do? All right, now I want to show you now I did show you this last time, but let me just introduce it as though I didn't. The correct probability density for energy is something that Boltzmann figured out. He was the guy that also figured out that equation for entropy. I didn't make a big deal of it last semester. It was SKB number of microstates. He did a little bit with it. His other major contribution to science was this. As I mentioned to you as well, the damnedest thing is that you can derive this, and that's kind of cool. I saw this like on my first day of class in grad school. So it takes all day. It does involve, have you ever seen the method of undetermined multipliers, Lagrangian undetermined multipliers? Whoa, none of you? Wait, no, really? Wait, none of you have seen Lagrangian undetermined multipliers? That's weird. Okay, I did see that in Calc 3 when I was your age, so someone is not showing you enough stuff. But anyway, the derivation involves this thing that none of you ever heard, and it's kind of hard. So we're just going to leave it at that. Now you know that I never try.
Is that different from the method of underdetermined coefficients?
That might be the same thing if they change the word.
Yeah, they may have just called it by a different name.
They called it something different. So who has seen the method of undetermined what?
Underdetermined coefficients.
Underdetermined?
Yeah.
Jesus, what kind of, anyway.
We learned the range of multipliers in Calc 3.
Oh, you did? Okay. Right, but it's a pain in the ass, right? So,
Yeah.
Yeah, and when it's applied to this, it's also a total pain in the ass. I just want you to know this is derivable. This is derivable. I'm just not going to do it. You know, I hate that. I want you to know that all of this comes from things, this comes from the laws of conservation of energy and mass, and I'm pretty sure that those are true. They were last semester. So if energy and mass are conserved, then this is correct. but I'm not going to show it, and you know how loath I am to do that, but I just don't want to blow out a day doing pure math simply to prove a point. Well, actually, I'm going to do that all the time, just know this. Okay, so this is the correct equation, which I'm just going to throw at you, and you just kind of have to accept that. And again, I'm trying not to do that as little as possible. And what this is now this is a density. This is a density, but you notice I don't have any partials there. Where's the partial of E? That's because it's a density, but it's a slightly different one. It's a discrete density. That means that, it's a discrete density versus a continuous density. A continuous density would be like for velocity, because we think that an object can go from 0 to 50 miles an hour continuously. It can take the car takes any value as it speeds up. This is slightly different. This says that energy occurs in steps. Now, it turns out that as we learn quantum, this is actually correct. This is always correct. Nature does not have continuous distributions. They don't exist. So when you see a car, what's that? I don't know what that show was with the British guy in the cars. I never got into that. But whenever you see a car speed up real quick, what was it called again? Top Gear. Never watched that. I didn't quite, maybe I should watch it. I know it was really popular. I just didn't quite see the appeal, but then I never watched it. But anyway, okay, so they're in a dragster and they hit the gas, they go real fast, and of course it looks like it's slowly speeding up till it's going very fast. It's not. Swear to God, you will learn this. So I'm speeding up. In my footsteps, by the way, not that any of you asked. Next to last doctor visit, I'm almost okay. Anyway, what's happening is, I know it appeared that I'm at rest and I'm slowly speeding up. I'm not. What's happening is I'm at rest, and then in the blink of an eye, I'm going a certain speed. And then I'm going at faster speed, and then I'm going at faster speed. That is actually what's happening. It's just that those jumps are imperceptible. They're so small, you're not perceiving them, but it's true. And I'm really foreshadowing here. We're going to be doing this in 6 weeks. The reason is that I have walls in front of me, and behind me. That's actually why that's happening. So that's actually how things work. It's just that those steps and those jumps in speed are so small, you couldn't even measure them. If you had some super laser device, you could not measure it. It is unmeasurable. I mean, I know what the derivation is like in terms of the jumps of speed. I can calculate it because I know my mass and I know the size of this room. Those are the inputs. And the jumps in speed are like unmeasurably small. If I was an electron, that's not true. Then you could measure it. In fact, we do. And that's how we know all this. That's how we know stuff like this is correct. That's how we know all this quantum stuff is correct. Anyway, okay, so I'm kind of babbling. We are getting there. I just wanted to foreshadow a little bit about how quantum mechanics works. Everything occurs in discrete energy levels. And actually, let me give you one last example. When I was writing my notes before class, I realized that we had covered this at one point. Remember, we talked about the internal energy of vibration. Remember when we were talking about the equal partition theorem, and we talked about how vibration doesn't contribute to the internal energy. And I mentioned to you, and you should have seen this in organic class. You should have seen maybe a little bit of this in freshman, that when you are looking at vibration, you have discrete energy levels. This explains the kinetic isotope effect. So if I recall, it was covered in quantum. And so something that has a CH bond vibration has this much energy. And if it absorbs infrared light, it then pops into another quantum state with a different energy. That energy difference appears at 3,000 wave numbers in an FTIR spectrum. So maybe you've seen that before. If a bond has a lower frequency absorption, it's very simple. The potential energy surface is just wider, and that makes the energy spacing more narrow. And that means that the absorptions for this vibration, this is, say, a Ci bond, carbon iodine, that would be a very, very floppy, very low frequency bond. And so it's got a wider potential energy surface. and that means that the frequency drops are less and it appears at a lower energy spectrum. Okay, anyway, what I like about this is that I can literally read off the energies from a quantum mechanical calculation or a Google search. You can Google this, you can find what the energies are, and you can plug them into this calculation. Now, you know the probability that a molecule is in the ground state or first excited state. That's what you can get from these kinds of things. All right, but then one of you had to ask me, so anyway, so now I want to do something kind of tractable. And let me also back up, because what you once asked me, what's the point of any of this, right? So, and that is a good point. Where are we going with all of this? And I think, didn't I do an okay job? Kind of, from that point on, I tried to stop and say, oh, okay, hold on, what's the big picture? Why the hell are any of us even showing up? Okay, so big picture before we spend the rest of the time on an equation that stretches across the board twice. So nature divvies up energy in this way by this equation that I won't derive because it's a pain in the rear end, so that's pretty powerful. It's also statistical in nature, and as we work with as we enter the land of the small of, the world of Ant-Man, then you have to no longer deal with like mechanics, like physics mechanics. It's now quantum mechanics, and everything is statistical. It's a mathematics of statistics. So that's very different than like mechanics, where anyway. So there's another thing about this is there's certainly a content of being a physical chemistry class. So I'm going to plug in velocities. There's also the fact that velocities are tractable, so that I can plug in velocities into this equation and we can do a lot with it, and it's not too hard. There's also a few, there's some examples that are specific to velocity that are kind of cool. I mentioned to you last time, we're going to do this on Friday, or maybe it's Monday. Molecules are moving faster than the speed of sound, even in the air. The speed of sound is about 350 meters per second. Most molecules are moving faster. It's like a cool factoid. That's it. In fact, maybe we don't need to do it. I just told you. There's some other things. There's other manipulations of these statistical analyses that give you very interesting information, more than you may realize you can get out of these things. And so I'm going to show you how to do that with velocity, but they certainly apply to other things. Question?
Yeah. So for your equation there, if you sum up all the different energy states that a molecule could be at, for high energy states, that's going to be weighted more to that sum.
Weighted less, even the minus. Right. Actually, it gets killed off real quick. If you plug in the energies, room temperature, this would be about 200 wave numbers, by the way. And now in FTIR, what are typical wave numbers? Do you know off the top of your head?
2,000.
Yeah, 2,000, 1,000, 2,000, 3,000, 3,000 it stops, that's, anyway. Right, so 2,000 over 200 is e to the minus 10. How much is e to the minus 10?
Very small.
Yeah, right. So when you're doing this calculation for vibration, you actually only need to include 1 or 2 levels, and that's it. So it's actually really easy. Yeah, well, that's one of the things I want to also get across. I've warned you many times you're going to write equations all across the board. Often they're just, half of it's just a bunch of constants. Not that big a deal. Any other questions? We're okay? All right, so now as I mentioned, energy, the energy I'm going to plug in, there's all kinds of energy. There's the strong nuclear force. That's what holds nuclei together. If you think about it, protons next to protons, that's a lot of charge, and it's the same charge, so they're right next to each other. Those are like, if you ever do a calculation from like physics mechanics, what is the force? And it's a repulsive force of 2 protons that are like a 10 to the minus 15 meters away from each other, and the answer is like a nuclear bomb. What holds them together is the strong nuclear force. I could put in the weak nuclear force, that gives us radiation. Gravity, that's incredibly weak, but unexplainable. Electrostatics, that's actually 99% of everything that holds or works together is electrostatics. I can plug all of those in, and we could do things with them. They're kind of difficult mathematically, but if I do this instead, if I do this, then I'm describing gas molecules. And to be blunt, we can do a lot with this, and you learn a lot from it. And you learn a lot about gas molecules, not that you didn't last semester, you'll learn a little bit more. But like I say, it has the benefit of being tractable, doable, without being too difficult. More importantly, in the big picture, you learn small things like molecules move faster than the speed of sound, which I know I can't stop talking about that because it's so weird. But there's also, I'm going to take the time to point out some of the more transcendental results of these analyses that would apply to other things. You're not going to be studying the speed of gas molecules in your careers, but you might do other statistical things. And so I'll point out when we get a more bigger picture thing. Okay, now I also want to point out, because I know what I put on the homework, so I wrote it. I just mentioned that this is a gas molecule because you said, but there's all kinds of energies, right? There's potential energy. Okay, now, if I'm describing a gas molecule, I know it can move, so I've got that energy. Now that I'm certain about. But the gas molecules interact with each other, right? Would that be, what kind of energy? You're the one who brought it up. There's kinetic energy and there's
Potential energy.
It's potential energy, right? Okay, now most of you were in this class last semester. What kind of gas is it when I ignore the potential energy? And that means ignore their interaction. They don't interact with each other.
Perfect gas.
Perfect gases. I describe a perfect gas if I ignore the potential energy. If I ignore it, it's a perfect gas. Now, if I ignore the strong nuclear force, it means that it never blows up in a Trumpian type of anti-hurricane. I'm not supposed to talk about this stuff, but anyway, if I ignore the strong nuclear force, it means that it never reacts in a nuclear bomb way, which is fine. If I ignore the weak nuclear force, the elements never turn to other elements by radiation. If I ignore gravity, then there's no gravity. Gas really isn't very strongly affected by gravity. So if I ignore those things, then they're not described, but they don't matter that much. Ignoring the potential energy of interaction is a little bad because real gases and perfect gases are not quite the same. And we talked a lot about that last semester, but they're not crazy off either. Again, I'm not worried about them going nuclear, so I'm going to throw that out. Throwing out gravity is really okay. So I'm just plugging in 1/2 mv squared into the energy, and there we go. So I'm going to be able to describe statistically the probability that a molecule has a certain speed. Now, and that's going to give the fact that molecules move faster than the speed of sound, but there's some other tricks. There's some other really kind of big picture things that we're going to be able to derive from that. And we're also, this is Monday, we're actually going to be able to derive the equipartition theorem. Yay! And who remembers what that is? Is it it rhymes with N and is anyways, none of you? Does anyone remember the equipartition theorem? 1/2 RT of energy per degree of freedom. Yeah. Yeah, oh yeah. Of course I knew that. Does that sound familiar, right? Remember, that's how you get internal energy. And then if you tack on PV, you get Helmholtz energy. You get enthalpy. Tack on TS, you get Helmholtz energy. Anyway, you forgot all that, but that's okay. That's why I will try to point out bigger picture things, because I know that it's not unreasonable. You leave the class and you forget stuff. That's fine, I do it too. I was actually almost fluent in Latin at one point, and I don't remember a word of it. It's kind of odd. Okay, now as I promised you that I'm going to write equations that go across the board, and this is one of them, and it's going to look really scary, but don't worry too much. We're going to whittle it down. It will start out kind of bad. Now, you're going to need a whole page of your of your notepad there. Okay, so again, the probability, sorry, I'm not writing density, this is a probability density of energy. And let's see, now, I'm not going to put that little subscript I anymore because I've gone from a discrete to a continuous. Remember, discrete is correct, it's the quantum mechanical thing. But when I go to velocity, I'm going to go ahead and call it continuous because it practically is continuous. And that's why I'm going to have mv squared. So I'm not putting like a little v sub I, excuse me, a specific velocity. When I don't put a little subscript, a little I, I'm saying it's now continuous. And here's the half, 2 kBt. And look out in case I forget the kb. I may forget the little b sometimes. I'll try not to. So there's the top part. Now the bottom part is the summation. And now I've got a bit of a problem because I'm trying to sum something that is now continuous. I went from the discrete Boltzmann thing to now the continuous. And so now I've run into a little bit of a problem. Hopefully, now, folks maybe after class tell me it's in the back you're having trouble seeing. Okay, now, again, I've already stepped on the landmine because I've, sorry, I didn't write that. I stepped on a landmine because I'm writing the sum of something that I'm considering as a continuous variable, unlike what I was just blabbering on about 10 minutes ago about quantum mechanics. Okay, so fine. I just took energy and I wrote 1/2 mv squared. That's all I've done. All right, so your head should not be blown off, not yet. Here's where your head's going to get blown off. Okay, whenever we're analyzing velocity is a vector. It's a vector because you live in 3 dimensions. Remember, I wrote down a minute ago. No, I deleted it. It was hiding. I wrote it a minute ago that velocity squared is actually vx squared plus vy squared plus vz squared. All right, you live in 3 dimensions. You can't ignore that, or have you? I contend that we're going to just do the bottom one, and then we'll worry about the top one. Let's do the bottom one. I contend that I am doing a one-dimensional analysis, as though we live in 1 dimension, like we all live in a straight line, which would be bizarre because we couldn't see each other anyway. But I've written v squared, which would be net. Which is it? Who thinks that this is really, I might as well call this vx squared, because it's one-dimensional. However, what is written is v squared, which would be, you kind of think 3-dimensional. What do you think? Is it 1D or 3D? 1D.
3D.
Okay, it's a split. Now here's why it's 1D. And this is actually kind of funny. This is technically one-dimensional. And you live in 3 dimensions. I'm telling you, this isn't right. The reasons it's one-dimensional is that there's only one sum. There should be 3. It really is that simple. Now, here's how I can turn this. I know what you're doing. You're looking at that beam and you're thinking, no, that's net velocity. Net velocity is 3-dimensional. Well, I put a little x there and now it's 1-dimensional. Right? Now, of course, you know, if we were Russian like our president, then we would be in Cyrillic, so letters don't matter, right? So this label is arbitrary. It is true, though, I am telling you the absolute truth, that, told you, that it's because I've only written one term that it is one-dimensional. It is actually that simple. Okay, to turn this in 3 dimensions, and again, it must be 3-dimensional. It has to be, because here we are.
Professor?
What's that?
If you have a summation on the left-hand side and it's not VI for different things, what do you change in the sum then?
Okay, so I'm getting to that. Right. If it's not discrete, like a table of numbers, like imagine that I look at those vibrational energy levels, and I have, and you can Google these, you can look at the numbers, 2,000 wave numbers, 4,000 wave numbers, and of course the jumps are 2,000 wave numbers. You could table those and then do that sum, and you would very quickly converge to a value. Velocity doesn't come that way. I mean, if I'm talking about a car going from 0 to 100 miles an hour, What do you do? 1 mile an hour plus 2 mile an hour plus 3 mile an hour? What about 0.5 mile an hour? What about 1.5? What about 1.25, 0.5, 1.75? Right? It's like, what do you sum? It's continuous. My contention is that I am not writing this out correctly. This is a mistake. So I've made one mistake writing the sum of a continuous variable, and I will fix it. I've also made the other mistake of being one-dimensional when I have to be three-dimensional. So, and let me write this out, and I'll explain a little bit more about that, and then we're going to fix that part. So, I'm glad you guys are thinking ahead. I will just get to answering this right at the end of class. And my handwriting will definitely improve. I've noticed this, I've done this a couple of times. My handwriting is really bad when I come back from break, even Christmas break. It'll get a little better, sorry about that. So now let me also point out that these limits, which again are strange because of what we were just talking about, these are vectors, so they can be negative. Remember when we were talking about velocity before, I was talking about net velocity and the limits were 0. There was no negative net velocities. These are vectors. They can be negative. And that's because things can move backward. That means something. There's no backwards when we were talking about net velocity. I'm going to talk a lot more about that next week, but I just want you to make sure that you know that. Okay. So that's the correct, now I've solved the fact that I'm in 3 dimensions. Now, I don't want to make a big deal of this. Don't feel you have to memorize this, but the way that this comes about is because of this. This is what I've done. So it's not like I'm just writing it down. I'm actually doing a derivation. And you know, e to the a plus b plus c is equal to e to the a, e to the b, e to the c. Right? So anyway, so I've actually, I'm not messing things up or just kind of creating equations. If you plug in b squared, bx squared, by squared, bz squared, you actually get this. Again, the limits are minus infinity to infinity because things move backwards. And it's also across the board, and it's hopefully giving you a headache. All right, questions?
Are we multiplying sums or?
Yeah, that was my question.
Okay, well, now, hold on, let me, in case it's not clear, let me just write it out. E to the a plus b plus c, where of course a and b and c are bx squared plus by squared, bz squared, is e to the a times e to the b times e to the c. So, what's the answer?
Okay, yeah, multiplying.
They're multiplied, correct. I'll have that like in the cheat sheet on the exam in case somehow that comes up.
Is putting infinity compared to the speed of light the same thing then?
I should not be going beyond the speed of light. Yeah, I'm actually going above the speed of light in the summation. Now, just like we were talking about here, let's e to the minus infinity. Right, so it doesn't matter. When you start, if you really do sit down and do calculations on this, the higher velocities, like when you're approaching the speed of light, don't contribute at all. It is technically, though, a mistake. I should not be writing infinity. Nothing can go to infinity. It's just that once you get to about 4,000 or 5,000 meters per second, which is really freaking fast, but still nowhere near the speed of light, the e to the minus things is killing a lot. So you don't have to consider a question.
Yeah, so if things are going, you said the molecules are going faster than the speed of light, why wouldn't those contribute more heavily?
We just talked, they could e to the minus that.
I know, but you said that the molecules are going faster than the speed of light.
Sound.
Sound.
Not going faster than the speed of light, right? No, they're not getting, you're right, they're going at the speed of sound. Speed of sound is around 350 meters per second. All right, so.
You see vision at the speed.
Well, they would actually get infinitely, well, for one, it takes infinite amount of energy for things with mass to go to the speed of light, and they would also get infinitely heavy. They would swallow up the entire universe in the process. So, not going to happen. So, okay, real quick, because I do want to set this up for next class. Let me do one of the terms. And all right, so I've solved the dimensional part. But now there's this summation part. And I mentioned the reason that this, I'm just going to do vx squared. The reason I mentioned that this is a problem is that, what exactly am I summing, right? When it comes to discrete energy levels, it's sensible because I probably have a list of energies. So I'm just going to do one of these. D squared of 2. Okay. I'm going to handle now the discrete sum, which is wrong. Again, like what are you adding? 1 meter per second plus 2 meters per second? What about the in-between spaces? That's why continuous can be is a major problem in the sum. Okay, now this is something I could spend all day on. There's this mathematical identity called a Riemann sum. Have anyone heard of this? Riemann sum? Riemann sum. Yes. No, it's a Riemann. It's like Riemann. My cats laugh at my jokes. Anyway, and now I forgot, how do you pronounce it again? Riemann sum. So you've done Riemann sums?
Yes.
Okay, all right, so this is a Riemann sum. Riemann sums turn sums into intervals. Right, now when you saw these, you probably saw an example of Simpson's rule of taking a function that has certain discrete areas, and then you just sum up those areas, which is great, so you understand how integrals really work. And I had you do that on your homework, by the way. You have a slight problem with a Riemann sum in this thing right here, turning into an integral. Here, let me just, notice I didn't turn the top part to dx, dy, and dz, and that will be made clear next lecture. If I'm going to apply a Riemann sum, for those of you who don't know that, you can turn sums into integrals. You can turn them into integrals. So I can turn this into an integral, but it comes at a weird expense because technically I've got a slight problem. I got a slight problem with this sum, turning this sum into an integral. Riemann sums have two terms. A Riemann sum works like this. There's a sum of a function, and usually there's another part of it that goes as like delta x, and that delta x can be made very small. And so this is the formula for a Riemann sum. I mean, it's kind of obvious if I write it this way, if delta x is very small. Okay, now again, you can Google this if you want to know more. I don't really want to spend a lot of time on this because, again, I could easily spend all day on it. Here's the trick. This thing has the f of x part, but the delta x part that is necessary for this to apply to the Riemann sum formula is not there. Here's the trick. Write it anyway, but put it on top too. Multiply and divide. That's the trick. It's stupid. Actually, I only figured this out just a few hours ago. You know what I used to do? I just wrote it down and people just accepted it. But I figured out actually where it came from. Okay, let me just get rid of that. And now, and then we'll just end with this. By the way, now you can probably guess that these integrals on bottom, for one, notice that they're all the same. They differ by an x or a y or a z, but that's really not a big deal. I mean, it is not a big deal. It doesn't matter at all. And hopefully you folks can see. I tried not to write in this corner because I'm afraid people can't see. This integral here, it's a very standard integral. And regardless, that looks fearsome, doesn't it? Okay, so there you go. And let me show you the result because it's so simple. I know I'm running over. Let me just show you real quick because I just want to show you that this ends up being incredibly easy. Here, I'll just use this. It ends up being m over 2 pi kBt to the 3 halves. 3 halves over 3 dimensions. I really hate my handwriting right now. I don't know why it's so bad. So there you go. Again, those 3 integrals, you see that it gives you this m over 2 pi kt. 3 of them to the 3 halves, and I have flipped it over, by the way. This is, again, the numerator of the Boltzmann equation, and what we have to do now, next time, is deal with this triple partial. That triple partial is a problem. It's an x, y, and z, and yet my velocity is net. So next lecture, I'm going to turn that into net velocity, which is a pain in the rear, and it's been all lecture on. All right, everyone.